Good morning. Welcome to Krishna's classroom. We now continue with the three principles of Littlewood regarding the structure of measurable sets and measurable functions. Now let us briefly recall the three principles, and we have already proved two of them, and we are looking into the second one. In fact, we proved the first one earlier and second one in the third one in the last lecture, and now we take up the second one, which is embodied in the Lusin's theorem. So let us work on it. Okay, so let us briefly recall what are these. So let me just put the title here. Okay. So before we take up the statement of the Lusin's theorem, we briefly recall what the other two principles were, and the first one was concerned with the measurable sets. He simply said that every measurable set is, so the first principle was every measurable set is nearly a finite union of intervals. That is the first one, which concerned the measurable set. Now, the third one that we have proved out was concerned about the relation between what is called pointwise convergence of measurable functions and uniform convergence. So it simply said that every pointwise convergent sequence of measurable sets, measurable functions is nearly uniformly convergent. That means pointwise convergence implies of measurable functions implies nearly uniformly convergence or uniform convergence nearly. This is the sum and substance of the second principle or the third principle. Now we take up the second principle, The second principle says what measurable functions are. Every measurable function is nearly continuous. Now this is the one that we are looking at in this lecture. Okay, so let us now state the theorem for what are called simple functions. Okay. So the third one, this is contained in what is called a gross theorem. The third one is contained in the what is called the gross theorem. Okay. The second one is contained in the Lusin's theorem that we are going to. Okay. So let us take the second principle in the case of what are called simple functions. So we take up the simple functions. We use this result later in proving the part 2, namely the general statement of the Lusin's theorem, or what is called the Lusin's theorem. Okay, so let us state the theorem. This is for the sake of simple functions. I mean, this is on what are called simple functions. So let f be a simple function needless to say that E is a measurable set. Then for each epsilon positive, there exists a continuous function there exists a continuous function g on R and a closed set f contained in E such that for which f equal to g on f and measure of E slash less than. So that's the theorem for simple functions. We first state for simple functions and prove it for simple functions, and then we make use of this theorem to prove the Lusin's theorem, that is in the more general scenario. Okay. So let us prove this. But before we look at the proof of this, I'll give some idea of what it says. Says, so you know that simple functions take only finitely many values. So let us take a very simple scenario, but we have to generalize it. See something like, you take this as your b as an interval, and now you see that you have a simple function. So you have some partition of this, something like this. Okay, and on each of these sets, the function takes it's essentially the special case of a step function that we are looking at. Something like this. So this is not the general scenario is quite different, as you know, because the simple function need not be a step function like this. Okay, it can be quite involved like the characteristic function of all rationals on the interval 0 to 1. Okay. So now what it says is this, that you can construct closed subintervals of this such that, you see, it's something like this, that you have, see, you have this one, from here it is connected to place, so that corresponds to this, and then you have this one, and then you have whatever it is, and here it is going to be again somewhere something coming from, say, okay, something like this. So you see that the yellow one that you see is thin. So actually what you are doing is, it's a kind of patching up. Okay. So you have, say, F1, F2, Fn. These are closed subsets which are denoted by these ones, and then in between you can connect the steps through a continuous ramp. So that's the whole idea. Okay, but it's the general scenario is quite complicated, but this is just to give a feeling of what you do. Okay, so with that we'll start with the general case. Now don't get completely carried away by this diagram, because this is not the most complicated scenario. As I said, you could have functions like defined as the characteristic function of the set of rationals intersection 0. Such functions are there. So you see the approximation would become very complicated. So let be the finite number of distinct values that the simple function takes on the simple function f takes on. Okay, right. And let ai be the value f takes ei. So you have got actually this E is going to be the disjoint union of ei with ei intersection ek empty for I and this is so. You see that then f is well defined. Because on ei it takes the value ai. Okay, and you see that f is well defined. Are distinct. So now what we do is the following. There exists a closed sets. Now there exists closed sets f1, f2, fn such that fk is contained in ek fk is contained in ek and measure of ek slash less than epsilon. This is the choice that we need. So what you prove is that there exists closed sets with this property for k equal to 1. So each ek is approximated by a closed set fk, and fk is nearly equal to ek or arbitrarily close to ek in the sense of measure. Okay, that means the complement of fk in ek as measured less than epsilon by. Now what we do is we define what is f. Now F you define as the union of keys. So Fk. Now Fk's are all closed subsets. Therefore, F is closed. And F is contained in E, and what more you have is this measure of which is equal to measure of slash which is less than, because you see that it is epsilon by n, so n such constants are there, therefore this is equal to epsilon, less than epsilon. So we have found the particular F, which is a closed subset. Right. Now we have to define G on R such that G on F such that it takes values, takes the value AK on that's what I have done. Takes the value AK on now what do you do? And this is for 1, right? So this is something like this. So you have got E. Now on each of this we have, this is the Venn diagram I have. F2, this it is F1 over here, F1. Now you are taking the union of all this. Now on this Gx1, Gx equal to A1. On this Gx equal to A2. And on this is how you work it. I mean these are F1, F2, etc. Fn are all closed subsets of E1, E2, etc. So F is taken as the and so on, and F is taken as the union of F1, F2, etc. And F is closed, and that's what we said. So you take this way, since FKs are disjoint, G is properly defined on F. Further, G is continuous Why? Because see, there's a gap between F1 and F2. Okay, so to take any point in F1 and take a neighborhood of that, or you can choose a neighborhood of that which does not intersect any other twice. Okay, that is one can choose for any x Fi even if it is a limit point of Fi. Okay. What this is what it will draw the picture. So this is what you have. See, suppose Pg. Now what you have is you can chosen a so for any x belonging to Fj or any x belonging to Fi, you can choose a neighborhood which does not intersect Pg. Okay, so that's what I am saying. For any x belonging to Fi, one can choose a neighborhood which does not intersect union Fine. Okay. Okay. Therefore, these are disjoint, and therefore, to see that the function g that you have now defined on f is a continuous function. Right. Now g can be extended. G can be extended from a continuous function f on f to the entire real line. Okay. Now this is one of the standard results that you have, that you make use of. Okay. So you will be using what is called the Teets extension theorem. It's a special case of the Teets extension. Teets extension theorem. So G is now continuous on the entire R. What about G? G restricted to F. So we have successfully extended the what is called the simple function f to a continuous function on the whole of R, whose restriction to f is going to be equal to 10. Okay. Now we have already seen that the measure of E slash f is therefore that completes the Now what we do is we generalize this result for real valued measurable functions. Okay. Of course, the strategy must be now clear, because we have already seen that if you have a sequence of What I mean to say is that if you have a measurable function on E, it can be approximated as closely as you want by a simple function. This is one of the results that we worked out. It has been constructed, how the construction goes on. And therefore, once you do that, the simple function can be managed using this theorem. Okay, and then we manage the differences, okay, such that together, the function that you have defined, or the continuous function that you have defined as approximation to the simple function which approximates to the given function, as a approximation having the desirable properties. So let us state the theorem first. This deals with the second principle. Let f be a real valued measurable function on then for every epsilon positive, there exists a continuous function G on R and a closed set F of, it's a subset of E, such that G restricted to F becomes F and G is a continuous function. So this is the Vidya, and the difference between E and F is arbitrarily small or made as small as it is. And a closed set contains E such that F is equal to G on F and G equal to F on F and measure of this is the statement of okay. So instead of working on a simple function, we are simply replacing it by a measurable. Okay, and you know that all simple functions are measurable. Therefore, that's a very special case of that. But we use that special case to prove this general theorem. Here we make use of the fact that the measurable function can be approximated by simple functions as closely as you want. That's the whole idea. Okay. So consider the case where measure of E is finite. Okay. Now the extension of this result to the case measure of E is equal to infinity is simple, and we shall make some noise about it later towards the end of this. We shall make some remarks on this. At the end of this proof. So let us take the case. So assume measure of E is fine. So that's the case that we have. Now by simple approximation theorem, there exists a sequence of simple functions defined on V defined on E which converges pointwise on E. So that's the first step. Okay, that's what the simple the approximation by the simple functions, or there's a theorem that we have proved earlier which tells you that. Okay, so what you have is that, so you are given F, this is E, F is given, F is approximated by what you call a simple function. Say by a simple function. Now we can apply the previous result on Fk. So you approximate this by 1. Okay, so let us work this out. Let by the previous theorem, for Fn simple and epsilon by 2 to the power n plus 1, we may choose a continuous function Gn and a closed subset such that Fn is equal to F and measure of essentially the previous theorem. There the epsilon is now replaced by epsilon by 2 to the power n, and what you have is you are taking this simple function in such a way that so we approximate by f, there is an approximation by fn with the desired properties, and then fn is approximated by gn. Or you have now by Egor's theorem, there exists a closed set containing E such that the sequence Fn converges pointwise F uniformly on so F naught is somewhere, okay, not, and measure of less than epsilon. So we have used the Egor's theorem to conclude that there exists a closed set F naught containing E such that Fn converges uniformly to F. That's the goal. Now, what about these Fn's? Fn's are continuous functions. Okay, right? And therefore, uniform convergence implies it is converges to a uniform, it's to a continuous function. Okay, so let us work on that part. Now, what you have then is this. Now, define intersection what about F? F is closed. Fn's are closed and therefore so F is a closed subset of and F is of course containing. Okay. Now using De Morgan identities and countable subadditivity property of measure, we have measure of equal to measure of union when and that is of course less than or equal to epsilon by 2 plus E slash epsilon F naught is less than epsilon by 2 plus sigma n equal to 1 to infinity epsilon by and this is less. So measure of E slash F is equal to epsilon. Now F is closed, as I have said, already said, F is closed. However, the uniform limit of continuous functions is was further the uniform limit of continuous functions is therefore f restricted to capital F is continuous. Now finally there exists a continuous function g on R such that g restricted to F is equal to F. Such a function exists. Once again we are using Peeth's extension, right? And this function has the required approximation. So on F, g is equal to the given function, okay, and what you have is, now you see we have got the continuous function approximated. Okay, so that completes the proof of the Lusin's theorem. Now what about the case where measure of what one does is, the suggestion is you can write R as the union of n equal to 1 to infinity minus n. Okay. So this is a countable union of open intervals. Now you take E, so E you write as and call this, right, you write E intersection the interval this as En. Therefore E is now union 1 to infinity. And what more you have is that measure of En is Yes, Emily. Okay. Therefore, it is bounded. Now, work on each one of these. So, what you have is this. This is what you have. So, you have now a telescopic sequence. Okay. So, E1, E2, etc., En. Now, you see that you make use of this particular monotone property of the measure, and the result that we have proved for E a finite measure. So each En is a finite measure. Take the results, the previous whatever we have proved for the finite sets of finite measure, and then make use of the monotone nature of the measure. So continuity of measure on a monotone sequence of intervals, sequence of sets En of any measure. Now we can apply the previous result for finite for each En. Okay. What does it mean? It means that there exists subsets, closed subsets Fn of En, and you can show that actually these Fn's are all disjoint. And further, now you see you have the result available on this each of En's, and then use that to get the given F is on the whole of E. Therefore, it is defined on each of En. Therefore, by this extension theory, you see that you get the continuous function on the whole of R whose restriction is equal to N on which G equal. Now use this for all N. You can show that actually this En's there is a gap So you see that, sorry, these FNs are all separated. It's a disjoint unit. So note that. So you can use that, right? And they use this fact. So that completes the proof of the Lusin's theorem. Okay? So we have now completed the analysis of measurable functions. So we have now completed measurable functions. So the first part that we dealt with was how to define measure. So the stages were stage 1, concept of Lebesgue measure. Stage 2, concept of measurable functions. Now you see the stage is now set. The stage 3 would be integration. So stage 3 we will be taking up what is called the Lebesgue integration. So 2 parts or 2 stages we have completed. So stage 3 is now Lebesgue integration. Okay. Or what called the concept of so that completes the second stage of our work, and now we go to the main part of this. I mean, this is what we had been looking forward to, how to get a credible generalization of the concept of Riemann integral, which is applicable to a larger class of functions and satisfying some of the or addressing some of the shortcomings of Riemann integral. So thank you very much. So I will start with the concept of Lebesgue integral in my next lecture.